prove square root of 2 is irrational. Similar questions we have, you can change this number to say prove square root 3 is irrational, or square root 5 is irrational, square root 7 is irrational, and so on. And we can also prove cube root of 2 is irrational, cube root of 3, or cube root of 4, and so on. These are irrational. So that in this problem, proves that square root 2 is irrational is the classic proof in discrete mathematics and also in number theory. The proof technique we're using is called indirect proof, or proof by way of contradiction, because it's going to be very hard to prove square root 2 is irrational. Irrational means it's not a fraction. Well, we can easily prove a number is a fraction. For example, if you want to prove 3 is a fraction, all you have to do is to write 3 as 3 over 1. That's a fraction. Or you can, if you want to prove any expression is a fraction, you just have to prove whatever on the top is an integer, whatever on the bottom is also integer. Integer divided by integer is a fraction. But to prove something is not a fraction, it's not easy, because you will have to prove all the fractions we have, which we have infinitely many, and that none of them is equal to square root of 2. And that's impossible to do, because we cannot verify infinite many fractions that are not equal to square root of 2. So we're going to take an indirect approach. So we prove by contradiction. So we assume by way of contradiction, suppose square root of 2 is rational. Suppose that, so we prove the opposite. We assume the opposite is true. See what's going to happen. And usually we need to find a contradiction. If we find a contradiction to this statement, which means this is false. If this is false, that negation, square root 2 is rational, that would be true. So this is the approach we're taking. And so how do we find a contradiction? So we start with what's given. Let me get rid of these. So when you do the argument, you don't need to put that, but that's why we're doing this here. So if it's rational, then that means it's a fraction. Square root of 2, if it's a fraction, I can write it as a over b, where a, b are both integers, and b is not equal to 0. We also need to add an extra condition. The condition is the greatest common factor of ab is equal to 1. What does that mean? That means this fraction is reduced in its simplest form. So you won't have a fraction like 4 over 6, because 4 over 6 is not really reduced. If it's equal to 4 over 6, we're going to reduce it to 2 over 3. So this condition right here is very important, because the contradiction is going to be contradictory to this statement, this assumption. So next we're going to try to do, this is what we have so far, and we're going to try to find the contradiction. And one thing we can do is to square both sides. The reason we're doing that is to get rid of the square root. It's going to be easier for us to talk about integers instead of square roots. And we know from algebra, square of the square root is equal to 2. And square of a over b is a squared over b squared. And next we can continue to get rid of fractions to, again, because it's easier to discuss whole numbers and integers. So we're going to multiply b squared both sides. And 2b squared on the left. And this b squared cancels that b squared. And we have a squared. So this is the expression we have here. And all a and b are both integers. And we can look at this equation to try to find a contradiction. So when we look at this, when I see the left-hand side has a 2 times b squared. We know b is an integer, which makes b squared also an integer. The left-hand side is 2 times integer. From what we learned before, 2 times integer must be even, or you can call it a multiple of 2. So either way, so since 2b squared is even, or you should say a multiple of 2, because we do have for any number which is a multiple of 2, we have a name, special name, we call it even, but not what if it's not a, what if this number is not 2, what if it's a 3, then you cannot call it by a name anymore. We don't have a name for a multiple of 3. And so maybe if when you do other questions, if the number is not square root of 2, if it's a square root of 3 or square root of 5, and you probably would like to use this form. So to be consistent, or to make it example easy for you to follow later, so maybe I will not use the word even. I'll just call it 2b squared is a multiple of 2. If 2b squared is a multiple of 2, because a squared equals that makes a squared is a multiple of 2. Again, in this case, yes, you can call it even, but I want to make it an example that you can follow to do the other questions. Like if you want to prove square root of 3, square root of 5, square root of 7, because you won't get 2 there. And all you have to say is, if it's 3 here, you just say a multiple of 3. If it's 5 here, you just say a multiple of 5, and so on. Okay, so that tells left-hand side is a multiple of 2, which means a squared is also a multiple of 2 because they're equal. If a squared is a multiple of 2, and here we're going to skip a step here, that's something we proved in one of our home assignments, then a is a multiple of 2. And to prove this, again, it's like saying if a squared is even, then prove a is even. And you also have to use indirect proof to do that. You can have to assume a is not a multiple of 2, and then what's going to happen to get a contradiction. So this part of the proof is omitted because we did this before. Okay, so a is a multiple of 2. Then we can assume a equals 2k, where k is an integer. And we're going to plug this expression back to the equation we got so far. So we're going to have 2b squared on the left. Replace a with 2k, because we know a is a multiple of 2, a is even. That's why we can assume a is 2k. Now simplify the right-hand side. The left-hand side stays the same. The right-hand side, we got 4k squared using algebra formulas. And we divide both sides by 2, and to simplify this expression a little bit, so now we end up with b squared equals 2k squared. Now let's focus on this expression. It's kind of similar to what we have before. So the argument will be similar to what we just had. And looking at the right-hand side, it's 2 times the integer because k is an integer. If k is an integer, that means k squared is an integer. 2 times the integer, that makes it even, or a multiple of 2. So we can say a similar sentence, since 2k squared is even, or you can say it's a multiple of 2. That makes b squared a multiple of 2. B squared is also a multiple of 2 because they're equal. Again, we're using the same argument that we did before. If the square of a number is even, again, this means even. If the square of this number is even, then the base b is even. I'm going to call it a multiple of 2. So you can follow, you can also use this statement for other numbers, even if it's a 3 or 5. Okay, here's the contradiction. Now we have a contradiction. Previously, using this equation, we got a conclusion a is even, or you can say a is a multiple of 2. And using this equation, I got a statement, a conclusion. B is also a multiple of 2. If a and b are both multiples of 2, which means they have a common factor 2. So a and b have a common factor 2. And if you remember at the beginning, we assumed this fraction a over b is in simplest form, which means a and b have nothing in common except 1. But now we found A and B have something in common, which is 2, that's a contradiction. So we can say contrary, this is contrary to the assumption that we had at the beginning. When we picked the fraction A over B, we made sure the greatest common factor of A and B is equal to 1. But now we're saying A and B have a common factor 2. That's the contradiction. So the contradiction tells us this. When you get a contradiction, you pretty much can't stop, because the contradiction would tells us that, because how did we get this contradiction? This contradiction is based on our assumption that square root 2 is rational. If you, based on this assumption, we got a contradiction, which means this is impossible, or in other words, this is false. If this is false, then negation has to be true. So we proved square root 2 is irrational indirectly. So this is the argument. So if you want to prove square root 3, all you have to, you follow this proof here, the format, everything, imitate it. You just assume square root 3 is rational, and the square root of 3 you square, you're going to get a 3 here. If you get a 3 here, you cannot call it even anymore, but you can still call it 3b squared. If you have a 3b squared, then you can call it a multiple of 3, and so on. If a squared is a multiple of 3, then a is a multiple of 3, and so on. And if you have cube root of 2, and you're going to have to take the third power, take the cube both sides. If you take the cube both sides, and you are going to get something like, let's say you're going to get 2, if you do cube root of AB, and when you take the third power, and you're going to get 2 equals A third, B third on the left. And again, so this will still be, you will have A cubed instead of A squared. So we had A squared here, but if it's cube root, you're going to have A third is a multiple of 2. And then similarly, you can still prove A is a multiple of 2, and so on, to try to get a contradiction. So here is an example to help you prove the similar questions like square root 2, cube root 2, or so on, to prove these numbers are irrational.